was explained. Yeah, so as was announced, so this will be a series of lectures about integrability. I think apart from the people who are doing string field theory and trying to look for the integrability structure, it will be necessary to understand what's been done. The subject is also, in my view, the single most impressive accomplishment in all of mathematical physics. And this offers important lesson on how to solve a problem, how to solve a computational problem that everyone knew was impossible. In fact, how many of you have attended lectures on integrability in planar equal-force parameters? How many of you have read papers on integrability of planar equal-force parameters? All right. So, just as a bit of background, when I started grad school, this is a problem that everybody knew was impossible. And by the time I finished grad school, the problem was solved. So we're going to discuss. In fact, let me first make an outline of the line of development that we're going to discuss. It really covers the development on a subject between it's going to be between 2003 and let's say 2002 to 2010, which was really where most of the important results were obtained. So sort of the prehistory of this is that let's say the prehistory of integrability. There are two important papers in 2002. One is by Minahan and Zarembo. So this is one loop, equal-force parameters that uncovered the structure of the Heisenberg speed chain. And then there's the BMN, the Bernstein, Molestina, Anastasi, and that's that. Anyway, this is the PD wave, the equal-force parameters. And kind of these two papers laid the groundwork of the integrability story. The subject really took off in the 2005 paper by Beizert. This is, I think, arguably the single most important paper on the subject. The paper called the dynamic SU/2S matrix. It is look at it, it's a technical paper. It's all about spin chain and algebra. If you don't study the details of the paper, it's not clear why it's important. It will not be clear to the casual observer why it's important. But it's the single most important paper. This thing, there are kind of two important results that we're going to discuss. The paper that basically leads to development. Let me go like this. One is the exact, that's known as the exact Magnon dispersion relation, and the let's say the Magnon S matrix up to what's known as the dressing factor, which will about dressing factor. The second is what's known as the nested beta ansatz for the spin chain as relevant for equal-force parameters. Let's say call it SU / spin chain. I'm just giving out the names for now. All of these we'll discuss in detail. So this this thing about the Magnon dispersion relation and this S matrix. So basically, the idea is that you have a single trace operator, bunch of fields. You view this as a chain of spins, very roughly speaking, and we're going to look at sort of the political spin, which are kind of magnons propagating over a kind of a spin chain vacuum. And in the regime where the chain is very long, there's going to be, we can describe the magnon asymptotic states. Don't worry if you have never seen this before, we'll come to the details momentarily. So one thing you can do is to analyze the dispersion relation asymptotic states in the magnon and use it to try to extract information about the spectrum of the spin chain in the limit when it's very long. Up to this point, let's see. So the magnon dispersion relation does not assume integrability. But of course, the assumption that the magnon scattering on the long spin chain will be a factorized S matrix, there's a huge assumption of integrability that was first observed based on like explicit two-loop, three-loop calculation. I mean, three-loop is already very hard, but you can't really compute that all of that directly. But there are bits and pieces have been checked at three-loop and then at four-loop. And then the next development along this line is to determine the so-called dressing factor. So what happens is that it turns out that for this basic magnons, which we'll define later, the two-body, so under the assumption of factorized scattering, the two-body S matrix is going to be determined by symmetry. The symmetry is something already non-trivial. We'll discuss what that symmetry is. It's a so-called centrally extended SU2/2 algebra on this open, infinitely long open spin chain. And the S matrix will be determined by the symmetry of the overall phase factor. This phase factor contains all the non-trivial unknown information known as the dressing factor. In fact, this dressing factor initially was not known to exist. People made a naive guess to think, just assume that it was one because they happened to agree with all data up to three-loop order, but then there's a disagreement at four-loop order. So when I was gradually going to PITP, I heard that people are worried about the ADS-CIT being incorrect because there's a four-loop mismatch. That was the issue with the dressing factor, and this dressing factor was understood around 2006. There's an important paper by Beiser, Hernandez, and Lopez, in which they made a complete guess of the dressing factor based on strong coupling expansion. The strong coupling expansion, so this is sort of the so let me say this 1/λ expansion, that being the tooth coupling of dressing factor. I'll just call this sigma. You sigma is sig. 1/λ expansion of the dressing factor. This guess is to all orders. This is an extremely impressive guess. I'm going to discuss later, not today. We'll get to this at some point, where this guess comes from. There was basically there are two essential. Well, let's see. The most essential input is what's known as the crossing symmetry. And in some technical sense, I would say the crossing symmetry is probably it's one of the most important assumptions in the whole business, and it's technically not integrability. It goes beyond the standard notion of integrability. It doesn't follow from just having infinite number of conserved charges. There was this crossing symmetry it was also not true to understand what the crossing symmetry how it acts, and that was understood by a paper by Yannick in 2005. This Yannick paper, which is a very beautiful paper to read, also very technical. It's all about the Hopf algebra and stuff. But it kind of provides kind of the one little missing piece of recipe that led to this Euler guess. This Euler guess, initially when they wrote the paper, they said that it looks like it didn't match the weak coupling, even though it is sort of it agrees with the expectation from strong coupling, just based on general kind of expectation of the worksheet of the string. But then I think a few months later, there's a paper, kind of landmark paper by Beizert, Eden, and Staudecker, where they match to a weak coupling expansion. This match, this is all other. This is against the direct back to all other imperfections here. It's all based on assumption of integrability and crossing symmetry, and this thing not only kind of passes a non-trivial check at for loop order. There was, I think, I forgot at the time whether the for loop computation was done. But the most impressive thing in this paper is that it accomplished the sort of one of the landmark achievements, which was previously thought to be impossible. That is kind of contains the all order say exact to all order in the planar limit, all order cuts almost dimension. Of equals for Mills theory. So the custom was mentioned, as you probably know, it describes this rotating string, folded string in AS5, so there's a energy which is a component weight minus the spin J. In the large J limit, this thing goes like some universal scaling function times the log of the spin. This is well-known results both from the quantization of a classical string. Sorry, just a classical string. You can get it from a Namamoto. But this is also well known in the study of gauge theory. It goes back to deep inelastic scattering. You can even find formally in Weinberg that volume 2 that has this. You can see the log J, of course. But Weinberg doesn't actually talk about the large spin limit, but the formula is there based on the one loop calculation. So it's a very universal thing. But the point is that this coefficient, which is something, of course, you would calculate from Namamoto in the large strong coupling limit. Well, the Beizert-Eden Staudecker got it, have the exact result. By exact, I mean they wrote some integral equation that you can put on the computer and just numerically integrate and find this value of this to all that. In fact, when they first obtained this integral equation, which is now known as the PF equation, they were able to just numerically try to estimate how they behave the strong coupling and match with the Namamoto action results, which is well known by that point. That by itself was already spectacular, but shortly after there was a paper by the Princeton folks like Igor Klebanov and collaborators, where they did the better numerics. Just they took the integral equation, did better numerics, and they also pull off the next order alpha prime correction that also matches with the earlier results that Seitlin and Frolov and Seitlin copied. So this was kind of a triumph on integrability up to 2006. This was like kind of part one, the first installment of integrability. And I should say that in this development, there's important work by Arutynov and Frolov. After they stopped doing magic string theory, they started doing integrability. The Arutynov and Frolov, their papers on the subject are amazing. Like all the kind of little pieces of details about solid and configuration, all that were all cleaned up in their papers. Okay, so now the reason that they were able to do this was because essentially here you're doing large spin limit, so you're looking at spin chain with a lot of let's say spins, and so it's not of course it was very natural to guess this correct addressing factor, but this is still for the very long spin chain. I mean, how the heck are you going to get Konishi operator, which is the shortest spin chain? So this requires a leap of faith, but this kind of actually started. It's based on something that's again with this. The technology was produced in the 2005 paper by Beizert. Starting with this so-called nested beta ansatz, one can let's see. The idea is going to be the following. So first of all, you need to do one step better than this cosmonauts dimension story, because in this case, you only need to look at the special class of single trace operators. But actually, in order to go beyond that, it will be necessary to look at all single trace operators. This is essentially largely due to the work of Artyomov and Frolov in the series papers. This is around, I think, starting around 2007. The first objective is to get sort of on the very long spin chain, get the complete spectrum. Well, not solving for the spectrum, but to represent the energy eigenstates or energy eigenvalues in terms of the beta ansatz. And usually, if you read kind of introduction about integral spin chain, like the Heisenberg model, you get a false impression that the beta ansatz is something very simple, just kind of the phase kind of multiplying around the circle and to some. It's a technology that's kind of easy to describe in one lecture. But it turns out that there's a notorious complication of this. If you have a situation where your integral scattering, so integral scattering, is factorized by Yang-Baxter equation. The particle type, so the mass cannot change, the particle number is conserved. The momentum also cannot change. They always just kind of cross each other, pick up a phase. Well, not necessarily a phase because the particle type can change. So in a situation where you allow the particle type to change AB to CD, so normally, in your experience, you might say that, oh, if you understand, one type of particle generalized to multiple type of particle, just get a bunch of matrices. It's not so simple. Okay, so it's true they can write some matrices, but you have to try to diagonalize this eigenvalue problem. It is not at all obvious how to proceed. But apparently, there's a strategy of this which was understood going way back to, forgot exactly when it was, but due to C.N. Yang. So the C.N. Yang, way back, I don't know, in the 50s or 60s, has studied in one kind of the groundbreaking work in the study of statistical mechanics of particles in moving one dimensions. Just in a simple case of delta function, potentially he understood some aspects of this. But in the kind of the modern terms, usually referred to as the nested beta ansatz. I must say that this is a subject that I have been avoiding myself until recently, because the nested beta ansatz is it's kind of a monstrous thing, and it's kind of hard to literally kind of hard to understand. But I finally have recently understood what this is what really is. I think there's not going to be a very simple way for me to say what it is, other than giving the actual details. Roughly speaking, okay, let me just say, kind of still as an introduction, just say heuristically what it amounts to. It's this idea that so normally, if you have some kind of spin chain, you say that if you flip a spin and flip another spin, these are like two magnons. But now we're interested in a situation where there are magnons of different types. So you're going to kind of elevate. So this is, you kind of view this kind of magnon property in the background of this vacuum of the spin down as the sort of the. Okay, so let me draw the picture like this. This is kind of heuristic, but it's kind of important heuristics. So this description where you describe all the spins up or down, as well as I'm simplifying things. Okay, I will refer to this as a level 0 system, or the level 0 description. That's this picture. Okay, so there's going to be a level 1 description. In the level 1 description, you only keep track of the magnons. All right, so not a big deal. That's what we'll be doing. So let me say that these are particles. But now there are magnons of different types. So one of them, they can change into magnon of another type. I'm going to draw this represented by the arrow in the other direction. So then you go to a level 2, where you fix the number of magnons, but you only keep track of these difference in the magnon. And the procedure continues to level 3, and turns out to terminate at level 3 for this specific spin chain. So, and it turns out you can diagonalize the beta ansatz by forming the beta equation at each level independently. So it's something that's far from obvious, but it's one of the one of the most significant results in integrability. And it's as I said, it's something that always scared me before, but now I think I have a very clear way to understand what is going on here. And so this allows you to kind of formulate a complete beta ansatz for the but still in the limit of long speed chain. And then there's a further leap of faith on top of this. Which is probably kind of the next most important assumption, which is what's known as the mirror TBA. This was also due to the work of Artyomov and Frolov. The basic idea is that you have integral theory, and you want to pass from infinite spatial volume to finite spatial volume. How do you do it? Now, naively, you might say that you don't have enough information. You have a quantum field theory. If you know the particle spectrum in infinite space, you know the S matrix, these are asymptotic observables. Okay, it's not surprising you can, given asymptotic observables, you can deduce the spectrum of theory in a large box. But what about the small box? Well, there is a way in relativist quantum field theory, because there's a so in relativist quantum field theory, you can go from a large circle, so 1 plus 1 d. You can go from the spectrum theory on the infinite line to the theory on the finite circle by exchanging space and time. All right, so you consider the thermodynamics, and you'll be able to extract, for example, the ground state energy. Turns out for integral theory, you can extract not only the ground state energy in this way, but also the energy of excited states. But importantly, in order to do that, you need to know the complete spectrum of theory on the infinite line. Knowing a subsector is not enough. That's why I'm going to bother with all of this. But of course, now you say that this sounds ridiculous because the spin chain is not the relativist quantum field theory. How can you exchange space and time? It turns out you can, provided that you say that on this side you have the ordinary spin chain of equals 4 super nils, single trace sector. Other side you have the mirror models. This mirror model will be defined precisely, but there's some kind of miracle that goes on that makes this possible. So this mirror model is in some sense related to the original spin chain at level of the dispersion and S matrix by inlet continuation. Yes.
So one somehow needs to know the scattering at like finite temperature or something, because I have finite time circle.
No. On the left-hand side, well, no, you don't need to know the scattering finite temperature. You just need to know all the states of finite temperature. We're doing statistical physics. But you do need to know. Okay, so there is another non-trivial leap of faith, which is that you do need to know the spectrum of theory in the regime where the magnons are dense. So that's where integrability will come in. Okay, there's a big assumption going on there. So a priori, this S matrix description is valid when the magnons are sparse. But there's some huge amount of evidence with no clear a priori logical explanation that is actually valid also in the limit when magnons are dense, provided the spin chain is long. It's well understood that if the spin chain is close, it does not work. But as long as the spin chain is long, the magnon can be dense, and the same story still goes through. This is, in fact, very important to get discussed when I was dimension. So that's one of the big assumption. But the assumption has been checked in incredibly impressive ways. So I think there's no doubt that this is correct, but there's no derivation. This is one out of maybe I can like later make a list of the actual assumptions going on. It's maybe one of like the 5 important assumptions in this whole business. Interoperability is only one of them. Okay, there are several more. The crossing symmetry being one. There's this. You can pass through this dense Magnon limit, and then there's this mirror. All right. So basically, you need to study this. But let's say beta ansatz for the mirror model, and then you can do this transformation, and then you get then you get this. I think this was our Chernoff and Frolov 2009. So these guys really played a essential role in the part 2 of this integrability development. And then but this equation still look very complicated. They had to complete the kind of beta ansatz equation based on this mirror, so from which they can then in principle get to pull out the spectrum on a circle, but this still seems to be too tough to directly implement. The equation is very complicated. But then there's the 2010. The story was really kind of came to to its actual application in the paper by this is Gromov, Kazakov, and Vieira. This is when they took the mirror TBA equation of Artyomov and Frolov and repackaged in the formula Y system so that it's actually managed, so it has a kind of something that's kind of manageable and can be solved numerically. Actually, I think this was the Y system was proposed in 2009, but by them, but a few months later, they were able to get the numerics and get a Konishi operator. Now this conclusion looks kind of crazy because as you know, the Konishi operator is traced by phi I. This is the shortest possible closed-spin chain. How can you possibly start from infinite chain and get something about the shortest possible chain? It works. And in fact, before this, this sounds totally crazy. You would never believe that you'll get a correct answer looking at how complicated the intermediate steps are if it weren't for some intermediate consistent checks. So in fact, this mirror TBA stuff, I should say that before the complete mirror TBA equation was formulated, there was again important work by none other than Yannick, who supplied kind of the first non-trivial evidence that by this kind of swapping space and time, so to speak, you actually can capture correctly the kind of wrapping, so-called wrapping effects. In the case of Konishi operator, he basically took these. He basically calculated the leading non-trivial finite volume kind of correction due to this kind of wrapping effects. Used this idea of this mirror TBA and matched a non-trivial for loop calculation of Konishi operator with all the zeta functions included. Okay, so it's incredible. Okay, so that was just like a tiny piece of the whole thing, but that was a kind of a tiny piece of calculation that very impressively showed that it's not nonsense. Then before the full system equations were formulated and then numerically solved. Anyway, that's basically a brief summary of the players in the game. All right, so I think and it's important to understand the details. I think the more you know about the details, the more impressed you will be. So I think we will probably, let's see. I was hoping to be able to cover this in maybe like 5 lectures, but now that I laid all this out, I feel like it will take even more time than that. I think today maybe I'll discuss some of the prehistory before the Spicer paper, and the next time we'll discuss the Spicer paper on Wednesday. And after the break, it will probably take at least 1 lecture, maybe 2, to discuss this. Maybe I think 2 lectures for this development, and maybe 2 other more lectures for the next debate ansatz and the mirror TBA. So that's the plan. Any questions or comments? Yeah.
So what exactly is the input from string theory? Like,
I would say the guess. Okay, in fact, let me just mention where are the assumptions. So one assumption is the invariability, which is factorized as matrix. So this is assumption number one, I would say. The crossing symmetry and also an analyticity property of the S matrix. Note that this is, we're talking about the spin chains, the non-relativistic system. So analyticity itself is not at all obvious. This is assumption number two. There's a highly non-trivial solution to this. I should say that I should also mention that over here, in this development, there's the important story of Hoffman-Mondesina. This is a giant magnon, magnon that kind of provide the physical picture as strong coupling. And the explanation why you expect this crossing, which is something I should say that I want to emphasize that this crossing symmetry, I will have to explain what it is. It's not something you would have easily guessed from equals 4 supremos. In fact, it's intrinsically not perturbative from equals 4 supremos point of view. This crossing symmetry is better understood as strong coupling than weak coupling. And weak coupling, so this crossing symmetry simply cannot be defined at weak coupling. And so it necessarily requires working at finite total coupling, even in order to define what it is. Right, so that's something that really comes from the thing about string theory, even though the string theory is just providing the picture, but it tells you that this crossing symmetry should exist, well, at least kind of in a heuristic way. And then in this stuff here, there's this, as I mentioned, the so-called, the asymptotic beta ansatz. So you see, one thing that makes the literature on really hard to penetrate is because the experts often don't state very clearly what the assumptions are. But I'm going to lay out all the assumptions clearly. So the asymptotic beta ansatz, I'm going to call this ABA for short. This abbreviation is a little confusing sometimes because there's also the so-called algebraic beta ansatz, which can also be abbreviated ABA. But in this context, every time I say ABA, it means the asymptotic beta ansatz. So what it means is to try to diagonalize the integral spin chain. It doesn't mean the chain is long, but we're going to importantly, allow the magnon to be dense. So this is, I would say, this is assumption number 3, that you allow your beta ansatz formulated based on the estimation of the magnon to also be applicable in a situation when the magnon is dense. Now, I should say that in the literature of the usual spin chain, when people study spin chain with covered modeling one dimension, these things you can just prove exactly given the exact integral model. But here you can't do that. You don't even know the Hamiltonian to begin with. You cannot. So all of that is kind of assumption. So to be able to apply ABA in a regime when the magnon is dense, this is number 3. In this sort of method, beta ansatz, there's something known as the people call the string hypothesis. This string has nothing to do with the string theory I'm talking about. This is the string, so-called beta string, which is basically a hypothesis that you can get all the states in the infinite line and do this swap based on this nesting procedure. This is I can maybe assumption 3.5. This assumption is a bit technical one. I would say that it's something that you can more easily check than the other assumptions. And then the mirror TBA itself, the existence of this kind of mirror model and this relation, this is assumption number 4. I would say that these are the key assumptions that lead to the solution of this cognitive problem. In fact, you can ask, in addition to where's the input from string theory, also where's the input from equals 4 supremos? Well, the input from equals 4 supremos is the symmetry that leads to the dispersion relation. Or this SU2/2 symmetry. This is sort of, at the technical level, of course, we're talking about equals 4 supremos, but at the technical level, the only place where you actually need the equals force parameters Lagrangian is at that step. Once you have that dispersion relation and the symmetry laid out, you can just take off. You never need to touch equals for Lagrangian again. But many of the things said here has extremely impressive predictive checks at full loop order by people like Korchemsky and Saitlin and so forth, all the Russians to do the hard calculations. Yeah. Yes.
The symmetry or whatever between the mirror model and the cylinder, is it checked or is it still?
It's checked in extremely impressive manner. But check in the sense of checking the results. So checking the prediction on this wrapping corrections. But yes, it's checked in more impressive ways than you can imagine. There's almost no doubt that that is correct, even though obviously, it's very hard to try to understand how to actually derive it from first person.
So is it something that the string theory can see when the space and time spoke is like
Maybe. Because all of these spin chain, all of this spin chain picture, including the short spin chain, can in principle be understood from the worksheet. If you understand the worksheet, CFT, the pure spin phonos or something, people had, were hoping for that this never came to, there's no very concrete result having obtained from the worksheet description, but yeah, in principle, it's something that you should be able to understand from the worksheet. So you see, this swapping space and time, sometimes referred to as double wick rotation in this context, is very similar to the crossing, right? Because if you draw a picture, here, you have this X matrix. The crossing is basically rotating the picture by 90 degrees. A, B, C, D, and you view this as an antiparticle going in. So crossing is rotating by 90 degrees. That's basically like double wick rotation. So these two things are very similar. They're not technically the same. I would say that this mirror model thing is a even stronger assumption. There's a very technical sense in which it is a stronger assumption, but it's very much along the same spirit. And this, there's no obvious explanation from the spin chain point of view, because spin chain point of view come from weakly coupled equals force parameters, come from Feynman diagrams. So from the perturbed equals force parameters, it's impossible to understand why this is true. And I would say indeed that the natural explanation, if there exists at all, will have to come from the string theory side.
So somehow like these spin chains are like the worksheet. So somehow if I'm like
maybe in some gauge, yes. I mean, essentially, in the prehistory of this, the BMN was the first to recognize that the spin chain should be thought of as some kind of maybe string bit model for the worksheets. That was only had been made precise in some limits, I should say. So for example, in the limit when this is very long, in fact, the giant magnon is also about that, right? So the giant magnon basically means, let me just say that the picture, the giant magnon says the following. So Hoffman recognized that just consider the simple situation where you have a single magnon, this one thing propagating, all right? But you're going to consider this in a regime where you have a large Topf coupling. Now, what is the holographic duo of this? The idea is that the holographic duo of this looks like the following. So we've got ADS5 times S5. So we have a particle sitting in the global ADS5, just sitting still, nothing happening there. On the S5, it is orbiting around one of the directional rotation. All right, so I'm drawing this here S2 inside S5. So Hoffman and Malacina found the following picture for the dual description, that the string, okay, so if you didn't have, if all the spins are down, this is a BPS state. So that corresponds to a graviton moving with some large angular momentum in the limit was changed very long. Similar to the giant graviton picture, but this is before we get the giant graviton regime. This is still further, all of this is in the limit when n goes to has been taken to infinity, looking at. So when I say spin chain long, it's long compared to 1, but small compared to n. Right? We're still in that region. So not giant graviton. So the string will be point-like. But if you add one magnum here, the solution looks like this. The spin like this. Okay. And so all of this stuff is that one single spin. The rest of the infinite chain are these 2 points. Okay, so as you might imagine, the actual map between the worldsheet coordinates and the spin chain coordinates will be very non-trivial. I should say that in my string notes that's been constantly updated, up to all of that and up to this is already written, but I haven't finished. I'm in the middle of writing the nested beta ansatz. I haven't finished writing the mirror TBA sections, but that should be done in the coming weeks. All right. Any other questions?
What's the relation theory? It's just finding the Lex connection.
Sorry.
Finding the Lex connection, like Wolfen's or
that
anything.
It has something to do with that. That provided the motivation. But in this whole thing, that's all it did. It provided motivation and nothing more. And really all of that can be inferred. So maybe if you understand at the quantum level, we provide step number 1, which factorizes S matrix, but not the rest. Okay, so there's a huge amount of assumption going to this. That's much more than just having these infinite many community conserved charges. All right. Anything else before we? Yes.
So somehow from the string field theory, I will have like some like if I want to represent this like string with like one magnum excited, I will have like I will turn on something like psi, and then I will turn on something like del of something to like some very large number or something like that. It's gonna be like the vacuum and something on top of it, or like how is the various operator gonna look for this for the string, right? Very roughly. What was the picture?
Let's see. Do you want to stay near the magnum vacuum or no?
Yes.
Well, that would be a near BPS state, right? So if you're in magnum vacuum, that's literally a supergraviton state. So if all the spins are down, that's literally a model of the graviton. So that's the vertex operator you already know. Okay. Now, okay. I think your question is addressed most easily in the BMN limit. So I'll say this in more detail later, but let me just first sketch this now. What is the BMN limit? The BMN limit, the BMN, which is the prehistory to this, is the prelude to this exact magnum dispersion relation. So the BMN right here. So BMN is the limit of small momentum. Let's say magnums of small momentum. Okay. So it turns out if you're at strong coupling and have magnum at small momentum, that means this thing is very, very close to BPS, roughly speaking. So, if it's actually if it's a zero momentum magnum, then become BPS again. Right? So this is by asymmetric rotation. So the small momentum is very, very close to BPS. That means you have this string that looks almost like a graviton is moving at the speed of light. And you can describe that, but also the angular momentum, also the R charge is large because the spin chain is very long. So you're looking at the kind of highly boosted near graviton mode. So that's why you can describe that by this PP wave limit, where you just, or the Penrose limit. You zoom in near the null geodesic in ADS5 times S5, and you find the PP wave. Now that once you understand, you can take that PP wave limit, you can actually quantize the worldsheet theory because the Green-Schwarz string is Green-Schwarz action in this case is free in the Lycombe gauge, and so you can describe the exact quantum worldsheet states that correspond to the magnon in the limitless moment. Now, of course, if it's not a small momentum, let's say if you're going to the strand magnon picture, you need the full Walsh theory is not enough to have the PP wave limit. So then, you know, but the BMA will provide a kind of important hint as to what you should be looking for. So basically, from that point of view, every magnon is going to be a particular quantum of excitation of the Walsh fields in the Green-Schwarz description PP wave. So the magnet dispersion relation in that case simplifies from some weird non-relativistic dispersion with the square root of like 1 plus sine squared to a relativistic dispersion relation of a massive particle. That's how it connects to the Green-Schwarz.
So there's one thing that's confusing me. Like this whole thing seems about sort of scattering on like the string itself. So
Yes.
so somehow
It's all free string theory, actually, right? So all of these things, which is extremely expressive at the end of the day, is about the string theory in 8 times 5 in the zero coupling limit.
Right.
But of course, we expect that the string interactions perturbedly will still be governed by some of the structure. But all of this is so far about free string theory.
then I'm sort of confused. What would like target space, like some target space approach like string field theory, but what would it like tell us about
Well,
this
the
capability?
spectrum.
Because
The spectrum.
the spectrum.
Yes. So I mean, if you can compute the result of if you compute the mass of the condition operator, you'll be directly producing the strong coupling expansion.
But it wouldn't tell us about like this dressing factor and all these things, right? Because that's
Oh,
sort of,
well, that requires a more careful study of a long string. So yes, if you want to reproduce the dressing factor, you have to look carefully at the very long string. You have to have a large quantum number. But well, that's why I want to discuss this, because you need to know what to look for. All right. Any other questions before we? How long has it been? Oh, so already more than an hour. Wait, not 1 hour. Sorry, 1. Anyway, okay, so let's now talk about the actual details. We need to start with equals 4 supremous Lagrangian because we need to label the fields. So we need to set up our notation. Equals 4 supremous. Okay, so we're going to have UN, gauge group. There's Young's coupling GMUs. In my convention, I'm always going to define subcoupling to be twice GMU squared n, and with a specific normalization about to right. So the action is 1 over GMU squared integral. I'm writing this in the Lorentzi convention. Trace minus 1/4 f mu nu minus 1/2 d mu phi I. D mu phi I somewhere in 1 to 6 plus 1/4 phi I phi j combinator squared minus 2 lambda bar I gamma mu d mu lambda I. This capital I runs from 1 to 4 and plus I lambda I gamma I capital Ij. All right, so whenever I write a little I, it runs from 1 to 6. Little I runs from 1 to 6, right? And the capital Ij runs from 1 to 4. So anyway, let me finish writing this. By I and the j, that's I lambda bar by Ij by I lambda bar j, where the fields are phi I from 1 to 6. You got lambda I alpha, lambda bar, upper I, lower alpha dot. These are biospinners in the 4-dimensional notation. The alpha and alpha dot are 4-dimensional chiral and chiral spinner indices. And then, of course, you have the non-engaged field A mu. These are the fields. We will have a SO6 R symmetry under which the phi I is transformed as a vector, and the lambda I is transformed as a chiral and anti-chiral spinner. Here we have the 6-dimensional Dirac gamma matrices, and that's it. That's the one. Of course, we can add the theta term. The theta term is not relevant in the planar limit. So I'm not going to bother with that. Okay. Anyway, all these the details are already in the string notes already. Chapter 20. Okay. Let me describe the supersymmetry. All right. So the supercharges are Q upper I lower alpha and Q bar lower I alpha dot. So the i's are in opposite places as on the fermions. So just by matching indices, you can easily see. By the way, I can trade the vector with the bispinner notation. So phi I can be defined as have gamma I ij phi upper ij. So you can trade with the bispinner, and if you write in this way, this phi upper ij obeys a radical condition that says phi upper ij Hermitian conjugate. Because this phi is our Hermitian in my matrices. This is equal to 1/2 epsilon ij kl phi kl, which I define to be phi lower I. This is a standard convention. All right, so you have the supercharges, how they act on the field. Qi alpha acting on phi jk. I will not worry about the factor 2 here. In fact, for this, actually, you don't need to think too hard about factors 2s and signs, because later this closure of algebra will fix everything. So work very hard. So delta ij lambda k alpha jk antisymmetrized. That's this on the left hand side. Q I alpha a mu goes like sigma mu alpha beta dot lambda bar I beta dot. Q I alpha and lambda j beta. It's like delta I j sigma mu nu. It's the usual textbook notation. Four-dimensional spinor fields mu plus epsilon alpha beta phi I k phi j k. I mean, what else can you possibly have? These are sort of the only thing I write down, and I'm not keeping track of coefficients. So these things are easy to remember. And finally, Q lambda bar j beta gives you sigma mu alpha beta. Sorry, this is dot beta dot d mu. D mu being the covariant derivative by ij. And there's a similar thing for Q bar, where the bar and bar spinners are swapped. Okay, you can easily produce that. So this is how the SUSY acts on the field. Any question before we move on? Now, of course, there's an important fact that we have a conformal symmetry, and the conformal symmetry doesn't compete with supersymmetry, and therefore it generates superconformal symmetry. So the next thing we'll say, which is kind of a standard story, is the superconformal symmetry of N equals 4 supernomials. We'll need to, the superconformal symmetry will play an essential role. So we need to define the, to write at least write down the notation for the charges. So the superconformal algebra, which is also known as PSU 2,2/4, is generated by, so we got these Q's. And then we're gonna have the S's. Which kind of has the opposite chirality. And the non-trivial part of the algebra looks like the following. Find the formula. Well, just like Q, so QQ and the commutator is equal to 0 in the absence of central charge. And so the QQ bar, this is as usual, is minus 2 delta ij sigma mu alpha beta dot p mu. The Euro supersymmetry algebra. So and set QQ to 0, so it's Q bar. Similarly, S. Right, so it's the same thing with P swap with K. So this is minus 2 delta J I sigma mu alpha beta dot K mu. K mu is the supercomponent generator, usual. And the non-trivial thing you need to know is that Q with S. So Q with S bar is equal to 0, but Q with S is not 0. This anticommutator is equal to 2I delta ij sigma mu nu alpha beta dot J mu nu. This capital J mu nu, this is the Lorentz generator. Minus I delta ij epsilon alpha beta. D is the dilatation. In my convention, D is always I times delta times the scaling dimension. And then minus 2 epsilon alpha beta Rij, where R is the R symmetry generator. A standard fact that some people might be familiar with is that while the R symmetry is the outer orthomorphism of the supersymmetry algebra by itself, but once you extend the supercomponent algebra, the R symmetry is the inner orthomorphism. It shows up in the right-hand side of this anticommutator. And so the bosonic part, bosonic group is conformal group, so 2,4, so 6. But then the Q and S together supply 32 fermionic generators that completes the super conformal algebra, super D algebra. So all of this is the kind of standard. Any question before we continue? Yeah.
Why is the SJ beta dot instead of beta?
What was the question?
In the last anti-commutator?
No. I meant to. No. Sorry, there's no dot. No dot. There's sigma mu nu. Sigma mu is like gamma mu nu. Thank you. Now, of course, also famously, from this we can derive the unitarity bound, which is, of course, essential to all the story. All the representation theory is, derived based on this. And as usual, Q and S are conjugate to one another, or Hermitian conjugate to one another with back to radial quantization. Just like how the P mu and K mu's are conjugate to one another. All right. So the next thing we're going to discuss is the spin chain picture for the for single trace operator. So as usual, we're going to, of course, be using the state operator correspondence. So we're gonna freely go between the picture of the operator and the state of the supremum theorem on the three sphere is understood to be equivalent. And the dilatation operator in this convention is I times the Hamiltonian on the three sphere as usual. We're gonna be interested in, okay, so we have a local operator, O of X. And the complex. The 2-point function, let's call this O prime, will be written in this way, in the notation of the inner products on the back to the of the Hilbert space of theory on the 3-sphere. It's the same as this over 1 over x minus y to the power 2h. This is just the it's equivalent to the PPZ inner product definition. Right. So so if you just want to do perturbative field theory calculation, this is how you go between the, of course, coordinate function and the energy or the dimension of the operator. Okay. Now we're gonna, in order to get to the business, we need to choose some suitable basis of operators. We're gonna start with the scalars. So there are 6 scalars. We're gonna group them into 3 pairs of complex scalars. So we have the phi1, but the dot phi6. We're gonna group this into, this for now by xa. Later I'll change notation, but for now this notation is sufficient. So okay, so I'll just call them. Actually, for now, let me call them xyz. Phi1 plus I phi2, y is phi3 plus I phi4, and z is phi5 plus I phi6. But I will also call these xa, where a runs from 1, 2, and 3, so that some of the formulas are easier to write. Now, it is useful to let's see. Okay, so these xa's they transform in the 3 of a U3 subgroup of SO6 R symmetry, evidently. I think of I can C3 as opposed to R6, right? Unitary transformations. We're going to organize the fermions. I'm going to change notation. The fermions are going to be reorganized into lambda A alpha and chi alpha. So there are 4 fermions, 4 chiral fermions. They're going to split into a triplet and a singlet, by lambda and chi. Right, and we're going to focus on actually, let's see. Okay, so let's okay. We're going to focus on the n equals 1 SUSY subalgebra generated by Q alpha and Q bar alpha dot, which these are, so I'm changing notation now. So these are one out of the 4 supercharge set of supercharges, and these are singlets under this U3, so that Q alpha annihilates XA, and Q alpha XA bar, I guess XA bar will have a lower index than A alpha. So I guess this is in the 3 bar thing in the notation. Q alpha, lambda A beta is equal to epsilon ABC XB XC, and Q alpha and chi beta is sigma B nu F mu nu, etc. Okay, so I'm writing down the same set of supersymmetric transformations, but now organized in this U3 notation. Not a big deal, it's just a notation. All right. Now, let's discuss the how to organize this Gauge-invariant operators. So we're going to be talking about single trace operators. So the simplest class of operators you can write down are made out of the scalar fields. So let's write trace x a1, x an. It's well-known fact that if you symmetrize this and restrict to the if you symmetrize, so usually if you have a trace of phi i's, if you symmetrize the i's inside the trace and restrict the traces part, you have a chiral primary, you have a BPS operator. This is already automatic traces. Yes.
So where did the indices alpha beta go on this epsilon ABC term?
Epsilon. Sorry, alpha. Oh, sorry. I think I probably missed the epsilon alpha beta. I should, but I didn't. Okay. Yes. Okay. So here, if you symmetrize this, these are our chiral primaries, and they're protected by the representation is shortened and the saturated BPS found. There's kind of standard argument, which I think I will not go through in detail now, why they're chiral primaries, but roughly speaking, you can see that you basically don't want to have commutators inside the trace. If you have a commutator, you can write as Q of something, and that would not be a chiral primary.
Was it like 16 BPS or like half BPS?
They have BPS. These are the simplest class of shortened operators. In fact, all single trace operators of finite length, infinite limit, are in half BPS representations. I mean, all the BPS ones are in the representation that contain half BPS operators. These okay, let me just reverse that. For the very basic reason, what is the deal of this? The deal of this is single string states, and the only BPS ones are gravitons. So these are all KK modes that graviton for the BPS ones, and the non-BPS are all master string states like Konishi. All right. So these we understand the delta is equal to n. This is exact. And such a BPS found. So this is simple. Right? This people knew from the first year of ADS-CFT already. Okay. Now the game begins. We're going to focus on for now, just for today, the SU2 sector. This SU2 sector means picking an SU2 subgroup of this U3, roughly speaking. Its name is not very important. It will become obvious what we're talking about. I'm gonna write this X to be, so we'll have X1 and Z is X3 in some arbitrary choice. Okay, so let's pick this. So we're going to start with the operator trace Z to the L. The L is the total number of the Z's, of course, inside the trace. This, of course, is a chiral primary we just discussed. So that's very simple. And now we're going to start adding, or let's say replacing one of the Z with X. So the idea is that you're going to think of the Z as a spin down and X as a spin up. All right, so we're going to have the spin chain picture. Let's add one. So have this. So this one is BPS. Well, the second one is also BPS. Oh, minus one. Remember this. The second one is also BPS because it's automatically symmetrized because of the cyclicity of the trace. But if you consider X, Z, and Z, another X and Z, this is generally not necessarily BPS. Not necessarily. I mean, you have to diagonalize. There's going to be a mixing problem. So there's one combination of this that's BPS, but the rest are not BPS. Now, at this stage, you know, you might say that, of course, this seems like a hopeless task because you have many more fields, and you know, how are you ever gonna get to all of that, starting with such simple things? Well, this is one of the lessons that you must learn from this development, you know, one step at a time. It'll turn out that all the other things, in some sense, are either related to this by symmetry, some emergent symmetry on the infinite chain, or can be viewed as bound states. So the idea is that this X is one of the elementary magnons, and all the other magnons are either related to this by symmetry or are bound states. That's a picture that will emerge. So anyway, for now, we have this picture of the spin chain. This is you know, you don't have to use the spin chain picture. You can think about X and Z's, the same thing. But it will be useful to think about this picture once you're trying to diagonalize this operator. Okay, so let me let's discuss that. Okay, so you know, obviously the spaces of operators can be identified with the spin chain. In modulo, there's a gauge redundancy, which is that which comes from cyclicity of the trace. But that just basically means that, you know, momentum is equal to 0. It's like a flow string. Okay. So the dilatation operator, which is I times H, this H, which is the Hamiltonian of the angle towards Ramios on the free sphere, can also be viewed as Hamiltonian for the spin chain. Yes.
You said everything is related to these by symmetry or is bound state. You mean all the ones with as many possible X's?
No, I mean everything.
You think everything comes from the one with just 2 X's, or?
No. With of course many
Okay.
on the infinite chain can are arbitrary many excitations. But yeah.
You said any number of X's and Z's, but those are the only ones you have to consider.
There'll be these, and there'll be ones related to these by symmetry.
Yeah.
Yes, the symmetry will be this SU2, centrally extended symmetry. Now, once you have that, you have the set of basic magnons, and everything else will be bound states. But yes, in general, you need to have many X's. So you should generally the simplest picture we're starting with here. By the way, this is what I called earlier the level 0 description. We're later going to pass to level 1, even level 2 description. Different level of, you know, how we can elevate our, you know, thinking. But for now, we're going to have this. So you think of the operator you want to focus on for now, the simplest class of operators are going to be a few X's in a sea of Z's. So there's mostly Z's, just a few X's.
Just to make sure that I understand this like spin chain analogy. So every operator here is a side and a spin chain. And
No. Sorry. I should be more clear. Every here, this is a Z. If I turn this up, this is an X. All right. So all right. This will be X. Right. So this spin chain represents the operator trace of all this if I close the chain.
I'm just like I'm a bit confused by your equation 21.5. Just because you have like the trace like the number of Z states are not matched with the number of spin chain like with down spin.
Hold on a second. You mean the counting?
Yeah.
That's a typo. Okay, I should fix that. I think that was a typo. This oh yeah, that under brace is supposed to include the upspeed. Okay, I should fix that. That was just a typo. Yes. Any other questions?
So just to make sure you have talked about like why we're introducing that and what's
Well, in some sense, Okay, thanks for reminding me. Actually, well, let me say it now. The important fact is that this thing is annihilated by the QL, which is obvious. So that basically that's essentially the thing that's going to so this combined with that. Okay, so there's arguments that I spelled out in much more detail in the previous chapter of the string notes. Is that the chiral primaries are in one-to-one correspondence with a certain kind of Q cohomology. One has to be careful in defining this cohomology problem because it's generally not a single Q we're talking about. But roughly speaking, it's like we're saying that this operator is in a non-trivial cohomology, is a non-trivial cohomology representative. That is annihilated by Q and cannot be written as Q of something. And from that, you will know that this operator can be is necessarily in the BPS representation. So generally speaking, you see, what is a chiral primary? So first of all, a primary of supercommon algebra is an operator annihilated by all the S's, by lowering operators. Now the S's are generally going to receive quantum correction because you know how the Q acts, but you cannot know how the X acts. If the X acts in this naive classical way, then you have no anomalous dimension because the Q commutator S can condense scan dimension, so that cannot be. So S has to receive non-trivial quantum corrections. So given this kind of representation of course, whenever I write this, I mean some kind of regularized operator in the quantum theory. You don't know exactly how. You may not immediately know how the S's act on this exactly. So how would you know this operator is a primary? Well, you don't quite know that. Maybe it has to be corrected a little bit. But you can show that if you know that it's in a Q cohomology, then in the cohomology class, you can always find a non-trivial representative if it's a non-trivial cohomology element, non-trivial cohomology class. Anyway, there's a kind of robust argument that tells you that you can always, if this operator is of the type that's annihilated by some Q and cannot be written as Q of something, then it's in the same cohomology class. So up to some Q exact state, it'll be a primary that is further annihilated by some extra Q. So this statement that's annihilated by extra Q is a shortening condition. The generic primary is not annihilated by any Q. So acting with Q and Q bar generate all the supercohomology descendants. So if it's annihilated by some Q, that shortens the representation. So for example, if you know it's annihilated by this Q, but it's also annihilated by some S, you take the commutator, and any commutator you get, you prove that it's saturated BPS bound. I forgot to emphasize that point. Any other questions?
So does that mean the BPS operator is very necessary? We need to be careful in the definition. So you need to be careful what you mean by the BPS operator, because this term generally is defined in a way that's slightly sloppy. Whenever I use the term chiral primary here, I always mean the operator that is, first of all, a chiral primary, a primary of the superconformal algebra, and on top of that, they're based on shortening condition. By the way, this is actually this requires some careful analysis. So people often incorrectly say that for the operator BPS means that the operator is annihilated by some, let's say, the combination of supercharges. This is not quite correct. The correct statement is that there's a shortening condition. The shortening condition means that you can have several. You can have primaries that transform in the non-trivial representation of R symmetry, and you can take one supercharge act on it, another supercharge act on another operator, another supercharge on another operator, and the combination of that equals to 0. So the shortening condition can involve several degenerate primaries. Okay, so it's a bit more involved than just saying operator is annihilated by some supercharge. So you really have to think in terms of representation theory. It's this intuition that saying that operator is just annihilated by some supercharge, this will only take you so far. It's not sufficiently general, this discussion. Well, thankfully, the full representation of BPS, no, the complete BPS representations of this PSU 2,2/4 algebra has been worked on in glory detail. When I was a student, I had to look up this paper by Shiraz Minwala, which is a very nice paper. Actually, Shiraz wrote this as a student that can work out the representation theory, but it was very ugly to read. Now there's a much more beautiful summary of the whole representation theory in the paper by Clay, Cordova, Thomas Dumitrescu, and Ken Intrigator. This like 200-page long list of tables is a great paper. It has all the most important tables. You just look up the table, you'll see all the representations. I mean, the references I've given in the notes as well. Footnote, I have the references. Okay. Now we need to discuss the actual calculation. Right. So as always, we're going to be interested in the anomalous dimension because there's this operator has some scaling dimension. So the most stupid way to calculate that is to analyze the 2-point function, which is the standard textbook approach. So we're going to start with that. But the general expectation is, of course, that in a planar limit, this H takes the form of a perturbed expansion in the Topf coupling. By the way, earlier at the beginning I mentioned that the stressing factor there was all other guess. In this paper of Beiser, Eden, and Staudecker, one of the spectacular outputs, apart from the custom analysis dimension, is that once they have this all other guess for the dressing factor as an expansion in lambda, they saw that has a finite radius convergence, which is 1/4. This was itself a spectacular result. When we expect the planar perturbation theory has finite radius convergence, but to actually have that theoretic expansion and see that it's pretty spectacular. On the other hand, the strong clumping expansion doesn't have finite radius convergence. Strong clumping expansion, one of the lambda expansion is like alpha prime expansion string theory. That one is explicitly seen to be asymptotic and does not converge. But it's borrowed in the case of dressing factor. So I guess it means that there are no worsening incident corrections, even though it's an asymptotic series. Okay, so we expect this kind of thing, right? So H0 is the classical scaling dimension, H1 is a one loop correction, H2 is two loop correction, and so forth. Okay. Now we're going to do the one and only loop calculation in this discussion. Of course, it was very important that people went up to the for loop, but for us, we're only going to do one loop because the rest will be integrability magic. One thing you observe here is that if you were to take the information where the X is symmetrized inside the trace, then it should be BPS and there should be no anomalous dimension. Of course, that's a fact that you should be able to also verify in perturbation theory directly, and indeed one can. In a sense, you expect that the non-trivial contribution to anomalous dimension come from kind of exchange interactions between the spin, so to speak. All right, so we can see that very explicitly. Let's look at the following kind of. Let's imagine we calculate O with O bar prime, where O and O bar are both operators of that type. So a few X's sprinkled in the sea of many Z's. And let's not worry about cyclicity of the trace for now. So this operator is trace of so there's many Z's, and let's say there's X here and many Z's. Could be other X somewhere else, but let's not even worry about those. All right. So this operator, based on position, and anyway, that's coordinate. But this operator, I'll write this as there's a Z bar everything is barred. And there's gonna be an X bar somewhere, and the Z bar, the bar, and so forth. Okay, so let's calculate the 2-point function. Now, of course, you just at the tree level, the family diagram looks like this. Now, strictly speaking, I should fatten every one of these into the fat graph to keep track of the indices. But you understand that we're in planar limit, so only planar graph contributes. And these things all have to line up adjacent to one another. So I'm not going to bother with drawing the fat graph. It just looks too messy in the picture. I'm just going to draw the single line, use a single line notation. All right, so at tree level, you have to contract the Z with Z bar. Of course, sorry, at leading order, you have to contract the Z with Z bar, X with X bar. And in particular, if you've got this, if the X in the O prime is shifted by one position, then this doesn't work, right? There's no such fraction. But it would work if you use a Feynman vertex that exchange X with Z. And we indeed do have this Feynman vertex because remember we have a scalar potential, right? So the Lagrangian contains the coupling trace X commutator with Z. So in particular, this trace XZ commutator, X bar Z bar commutator. So this has the X and Z coming in different orders. So this contains, for example, a trace of XZ, X bar, Z bar, and a plus trace of ZX, Z bar, X bar. These are the two interactions that will allow you to change, to swap the position. If you read this, you have XZ, X bar, Z. So these are the terms I'm going to this, and you can convince yourself that this, at one loop order, this is the only thing that can move the X, so to speak. And only move by one side. Right. So if you actually calculate this loop diagram, you'll get the one loop contribution to the anomalous dimension. I'll write that in slightly more detail in just a moment. But you're going to learn two things. One is that this H is going to receive a one loop, namely the order lambda contribution, which is what I call H1 there. And that this H1 involves only the nearest neighbor interaction. Now, of course, if you consider a two-loop diagram, you can have next to nearest neighbor interaction, so on and so forth. But at L's loop order, you can only have L nearest neighbor interaction. Now, of course, you can try to draw a diagram and bring this X all the way to there, but that's not planar, so that's not allowed. Right? The only, at a planar, you can only kind of hop by one side at a time for each loop. So I mean, the actual calculation is a simple loop integral. It's kind of standard loop integral. So let me write. It's kind of usually more transparent in position space using position space Feynman rule. So let's say this tree level versus this at one loop level. You can calculate this ratio. This is going to give you a one loop integral. Basically, if you think of this as location at space time position X, the Y, this is the 0, and the loop integral is going to be d for Y, 1 over Y squared squared times X minus Y squared squared. So this 1 over Y to the 4th is the propagator for massless scalar in 4 dimension position space. Sorry, 1 over Y squared is the propagator of some factor to the 4 pi. You have two propagators from 2 propagators here, 2 propagators there. There's some coefficient which turn out to be lambda over 4 pi squared squared. And then there's some overall factor of X to the 4th because of the way I normalize this. And this, of course, is logarithmically divergent, so that's what you want. The result is lambda over 4 pi squared. So 1 over 4 pi squared gets canceled when you do the integral. You get the log of x over delta. It's just I'm using kind of a point splitting scheme, but it's not too important for some finite piece. And as usual, this we're talking about 1 over x minus y. It's 1 over x, the 2h, where h is h0 plus lambda h1 plus lambda square h2 plus the dot, right? Let me use the notation of the whole dimension. So, let me write this. It doesn't matter. So if I expand this out to first order, I'm going to get lambda h1 times the log of x. So we know that this logarithm in the spatial separation, the coefficient is proportional to the h1. So that's a very simple calculation. Now, you might say that in order to get the full expression for the h1, I also need to look at a case where this x does not move. It stays on the same side. Right? So you have the situation where you have x bar, x, b bar. In this case, you can also have a contribution like this. But in this case, you might worry that there can be more complicated diagrams like you can also have like gauge bundling change and all of that. And indeed, you will have all of that. But they can be calculated, they can be all determined without doing any extra calculation. Because you know that if you symmetrize x, this h1 has to vanish. So that's enough to fix the contribution when this x does not hop. So you don't have to calculate anything else. It's very simple. So this calculation is actually all you need to fix h1. So let me just write down the results for h1. It will be perhaps make it kind of obvious. So the claim is that h1 is equal to lambda. I pull out factor lambda already. 1 over 8 pi squared sum L from 1 to capital L 1 minus P L plus 1. The P L plus 1 is operation that hops that exchanges the spin on the side L and plus 1. Sometimes in the spin chain literature, people write like in terms of Pauli matrices, and then you can rewrite this P L plus 1 in terms of like something like sigma L dotted with sigma L plus 1. So this is where the kind of the Heisenberg XXX spin 1 half chain notation come from. In this terminology, this XX refers to the fact that you have it's kind of homogeneous with respect to the rotation, the 3 dimensions. If you think of this as spin as, in the think of the Pauli matrices as a spin operator, and the 1/2 refers to that it has a spin 1/2. Anyway, it's just some terminology, right? So this is known as the XX 1/2 model. This one, of course, is very trivial. This one guarantees that if the x is symmetrized, then the h1 evaluates to 0, as it should. Now, let's say, okay, okay, so once you understand that this is H1, you can try to diagonalize it and ask what is the actual spectrum operators. When I think when Minahan and Zarembo started deriving this, I don't think they had imagined they can solve this diagonalization problem for the full single trace operator spectrum. They just want to solve this very limited problem. In this case, they say, aha, we know how to solve this problem because the spin chain. And this is a well-known thing in the literature. This is like the simplest example of integrable spin chain where you have a non-trivial solution based on the beta. So let's describe this diagonalization procedure. Now, in fact, if you open up the integrability literature, there's a standard lecture by Fadiev on how to solve this model. It's actually quite complicated. It's not so simple, actually. You know, but that's partly because they were interested in solving this exactly for any finite chain, so like length equals 5. Okay, so you can't do that. It's a complete solution. It's very beautiful. In fact, this one many years ago when I taught 251B, I actually taught this, which I kind of regretted because it was too technical for 251B. But you know, it's a standard thing you can teach in graduate quantum mechanics. Okay, there's a very beautiful solution based on what's known as the algebraic Bethe-Ansatz. I'm not going to discuss that because for us, we're only going to interested in this long chain limit, and in this long chain limit, it's actually much easier to understand. You don't need all this complicated like R matrix formalism, which is kind of impossible to understand until you had to kind of write down the equations. So we're going to, for now, just focus on the limit of the very long chain. I should say that even though this model is well known to be exactly solvable for a finite chain, this is technology. This problem has been solved, has been beaten to death. This finite chain version of the Bethe-Ansatz is not going to generalize to the higher loop order. So the only thing that's going to generate to higher loop order is going to be the thing for the infinite chain, which is this asymptotic Bethe-Ansatz. ABA. Yes.
Just to be clear, when you say this model, it's as if all the higher lambda corrections were 0.
That's right. That's right. This is at one loop. When Minahan and Zarenko were doing this initially, of course, you know, they just want to solve this in one loop order. One loop order at the time, they have one loop order, two loop order, right? And, you know, very often in physics, people try to proceed by going to increasing higher loop order, and then you just the papers become more and more difficult to write, and at some point you stop. The thing that's unusual about this is that they didn't stop and actually solved the whole thing. Yeah, there's some lesson to be learned there. But the thing is, you also have to be clever. It's not just about doing brute force calculation. Let's see. I probably shouldn't go on for too long. It's almost 3. Let me just write down one more thing, which is that if you have a limit of a long chain, for now, let's forget about the cyclicity property of the trace. That can always be taken care of at the end by imposing like the kind of gauge redundancy. It's going to be equivalent to saying that the magnon must have 0 total momentum. But for now, let's consider you know, the state of a single magnon. All right. So I'm going to you know, this interaction is such that if I just flip one spin up, that's not an energy eigenstate, obviously, because if I act on with H1, it's going to move this. But you also know that what should be energy eigenstate because there's translation symmetry. So you should go to a momentum basis. So the energy eigenstate for the single magnon would be in the momentum basis, where the P is written as the state is sum over L e to the IPL times down, down, up, down, etc. Right? I'm going to use this notation where this is the L side, and of course for this you need this P to be 2 pi over L times the integer. Well, but I guess let me put out focus on the infinite change in mid. Let me not worry about that. So you can act on this with H1 and easily diagonalize it, right? You will find that H1 and P is equal to 1 over 8 pi squared. Well, this is a calculation that's so easy I can do on the board. 2 minus E2 minus I P is minus IP times P, which is also known as 1 over 2 pi squared sine squared P over 2. That is the Magnon dispersion relation at one loop order. So you got this dispersion relation. It looks, we can see that if P were small, so the sign squared P goes like P squared, it'll look like a non-relativistic particle. But of course, at order 1P, this is correct at this order. So the energy of the Magnon, if you include the classical scaling dimension, which is 1 for that object. Okay, at this point, it's kind of trivial whether you want to include one or not include one is a matter of convention. But it turns out there's good reason to include the one, as we'll see later. You say that here it's lambda over 2 pi squared, sine squared p over 2, plus order lambda squared. Right. So rather than this dispersion relation, you might try to guess what's the next two-loop correction. Well, of course, if you want to get that, you have to calculate two-loop diagrams like this, which is already much harder, right? And of course, people do that in the early days. You can try to do that, and that was the important input data. The thing is, we haven't discussed integrability yet. We'll discuss this next time. You might say that, okay, first of all, it's a fact that this model is integrable. What does it mean for it to be integrable? It means that these magnons, if you have two of them, they can scatter. The scattering is going to be non-trivial. They're not free particles. They're going to interact. But the scattering is going to be factorized. It's factorized as matrix. And it's also a consequence of having infinitely many commuting conserved charges. Now, you might say that, this is the kind of simplest interaction I can write down. It happens to be integrable. Maybe it's always integrable. Well, actually, if you have next to nearest interaction, you can easily break integrability. If you just change the coefficients by a factor of 2, you'll break relative coefficient by a factor of 2, you're going to break integrability. This is very easy to check just level of scattering of Magnon. You'll still have a dispersion of the Magnon, but you easily break integrability. So already at two loops, it's just the people have derived the two loop Hamiltonian, this H2, and check that it's actually integrable up to two loop order. That itself is already very non-trivial. So it tells you that something is going on. We'll discuss next time that this is one of the kind of a huge leap that was made possible by this 2005 paper by Beisert, is that actually there's the exact formula for this, which is square root of 1 plus lambda over pi squared sine squared over 2. Right. So we'll see that formula is exact. Well, strictly speaking, there's a function of lambda here. There's some kind of function of lambda where this function of lambda turns out to be equal to lambda itself. That's not something you can deduce based on integrability or any kind of symmetry consideration alone. So in principle, you might have imagined that maybe there's some correction. But even with that, so what that's been shown in the Beisert paper is that this relation will hold for some f lambda. You may not know what the corrections are, but it has to organize into this form, which is already very, very non-trivial. And this is going to be the foundation of everything to follow. This makes it possible to have analyticity. Just like when you have a square root of p squared plus m squared, you can have you can continue to complex momentum and so forth. This will allow you to continue to complex momentum. And this has a much more complicated Brand structure eventually. And so there's going to be a much richer analytic structure. But thanks to the hard work of people like Artyomov and Frolov, it's possible to actually understand them. Right. So I think we'll finish now and we'll continue on that point next time. All right. Any questions before we end?
So somehow, like, the idea about getting this square root, like, from the string field theory, we will just like start writing down the ball sheet diagrams, and then after some point we will realize it's like a spin chain, and then or like.
I don't know. I mean, I don't know how it's going to emerge. We'll have to see. Well, the most important thing is, of course, to know that this relation is there. There are a couple important limits. Let me just mention this now. as I mentioned, actually, I mentioned earlier, so actually now we know that the function is exactly equal to lambda. But this is, this doesn't follow from integrability alone. This is kind of integrability plus localization. Right now, we know it's actually exactly lambda, but it's been conjectured since the beginning, but the justification came many years later. So there are kind of two simple limits when discussed. One is the BMN limit. So BMN limit is when the p is small, so this becomes p small. So this becomes 1 plus lambda over 4 pi squared p squared. So that's the limit when you look at relativity dispersion. I mean, p small but lambda large. So that goes. So that's the that I would say was inside of BMN that already goes beyond this this one loop analysis. Even though in the BMN, most of the calculation was from the Green-Schwarz strings, so that was from the bulk, from the strong coupling end. Of course, at the time, they only know how to do one loop calculation. They observed that it's compatible with one loop that you get from one loop. So that was kind of already very, very non-trivial. The second limit is just finite p, large lambda, in which you get square root of lambda, this times sine p over 2. We'll get this formula from Navier-Goto action later. This is the giant magnet. So this is the Hoffman-Malzina derived just by using Navier-Goto action. You can do a lot of with Navier-Goto action. In fact, Hoffman-Malzina not only studied Ricci relation, you can even study the S matrix in your pair of magnons just using Navier-Goto in the strong coupling limit. It was very clever. So that provides some data in principle to test coming from the spin chain. Anyway, yeah.
Expect this to be integrable just for the fact that it's exponential or super switches.
No, absolutely not. What do you mean? The CFT doesn't mean it's integrable. What do you mean? There's no relation whatsoever.
I thought CFTs.
No, absolutely not. CFT have absolutely nothing to do with integrability. No. That means absolutely nothing. That symmetry has nothing to do with integrability. In fact, the CFTs are almost never integrable. The only exceptions are, first of all, equals force Ramil's, not at large n is not expected to be integrable. All of this structure is going to break at finite n. In 2 dimensions, people tend to think that CFTs are integrable. This is also completely false. The 2-dimensional integrable CFTs are rational theories. So rational CFTs are integrable. That is true. But anything that's not rational is not integrable in any meaningful sense.
You see that it's integrable at the point of scattering, or
Sorry?
you see that it is integrable by factorization of the scattering, or
No, the first evidence of integrability is that this itself is integrable spin chain. The second evidence is that the 2-loop order is also integrable. That is much more non-trivial. So in fact, when ABGM came out, there's a question of whether ABGM theory has a similar integrability. In fact, I think the first paper that can analyze. So in that case, the non-trivial, if I remember correctly, I think the non-trivial numbers I mentioned start at 2-loop order. In fact, I think that the first paper that discussed the 2-loop spin chain of ABGM was written by me with Gyalto, W. and Simon Jiangbi. I think there were 2 other papers on the same subject came out the same day, but they had the wrong statement. We had the correct statements. It was not obvious there because in there you have a 2-loop and you have the next to nearest neighbor interaction. If you change the coefficient by factor 2, you're going to break integrability. So the integrability, the evidence for that is really this brute force loop calculation initially. And on the other side, there's a motivation from string theory because there's a classical integrability of the string sigma model. So they kind of, from the 2 sides, you can try to make conjecture. But then, at the time, there was a lot of this effort of trying to, Whitten wrote a paper that suggests that, oh, maybe, whether pure Yaml infinite n is also integrable, it was not clear. There's all this story about the Yang symmetry that never, came to anything. So there's when this idea of integrable, this theory was likely integrable was proposed, many different ideas were explored. But the line of pursuit that I described at the beginning was the only line that was successful. There are many other pursuits trying to understand the symmetry of the various charges. They never led to anything.
Just to be clear, in this case, when we're talking about integrability, I'm thinking of this as, some ordinary quantum mechanical system with a given Hamiltonian.
You can think
I
of that.
want to think if like I set up a scattering problem, ordinary quantum mechanics scattering problem, then that scattering matrix.
Correct. That is correct. But on the other hand, as I mentioned at the beginning, the story goes far beyond that because it's with all this mirror TPA business, right? It's far beyond.
I mean, at the level of the current discussion, that's what we're meaning by checking that.
That's correct. That's exactly right. So, and this is unambiguous, right? It's not like you need to go and look for the constructor. You might say that, oh, how do I know I found all the constructor? Maybe here I have a theory. It's just the constructor very complicated. I haven't guessed it yet. But no, it's either integrable or not integrable. It's very easy to tell because the S matrix of magnons is either factorized or not factorized. You easily check.
Do I have to think of like setting up some wave packets out of these P's or?
Yes, but you can do all that.
Yeah, but
I mean, as I said, as you'll see, there are along the way, there'll be many steps which looked impossible until someone tells you it can be solved.
What step exactly did you think that was going?
The L to be large.
Yeah.
So the single magnon state does not exist on a finite chain. So I need to talk about at least two magnons, but I already have to worry about interaction. So once I start working on interaction, discussing interaction, well, you have to worry about what happens when the magnons on top of each other. And I'm gonna, at this level of discussion, I will not gonna even worry about that. I'm just gonna worry about the asymptotic states. So that requires L to be large. As I mentioned earlier, this problem can be solved for finite L, but I think that solution, at least for now, is not very relevant because the only part that's gonna generalize is the larger L. However, it is still relevant to the extent that it turns out that give you a check that this large L limit you can still allow the magnon to be dense. As I said, that's really not obvious. I don't have a very intuitive way to explain why you can allow the magnon to be dense because a priori you're just studying like asymptotic states and it works for if they're far apart, but if they're more magnons than the size in between, how do you know it's correct? That's a big conjecture, but it has passed many checks. These checks are very non-trivial. But they're also very indirect because it's like you make some prediction about something and you can check with some forward calculation. But these are kind of very special calculations about very specific quantities.